And now it's time to introduce the last keynote speaker, Professor Carla Chiasserini. So she is Professor of Electronics and Telecommunication at the department in Politecnico Torino. She has been there since the year 2000, and now she's full professor. She is IEEE Fellow, and she's been listed as one of the top Italian scientists in one of the rankings, and editor-in-chief in the Elsevier Computer Communication Journal. Her research interests are in the fields of wireless and mobile networking. So here we are in the domain of networking, but recently she has been approaching the field of multi-robot system from the point of view of networking. So we can talk about networked robotics. So Carla, welcome.
Thank you very much, Eliseo. So yeah, as you said, my field is actually wireless networks, and of course nowadays 5G that is also applied to robots, and in particular actually smart factories and industry 4.0. So I know that has been a long day for you guys. So this presentation is going to be kind of light, so no worries. I hope it will be clear, but in case of any question, please feel free to stop me anytime during the presentation. So I will actually start with a general, let's say, introduction about 5G and why 5G is important, and it can be also important for example, industry 4.0, smart factories. So first of all, what I would like to highlight is the breakthrough that 5G represents with respect to previous generations of cellular networks. So the key point here is that 5G is supposed not just to transport data as the previous cellular generations, but to support services that are required by vertical industries and that should be provided to mobile users. And so here we have the famous triangle proposed by ITU, and essentially summarizes the strengths of 5G, like the ability to provide a very high throughput, so broadband communications, and then massive machine type communications. That means lots of simultaneous connections that can be supported between machines and the network, or users and the network. And then of course also the low latency, very low latency, and high reliability. So this is in particular very important, as we know, in smart factories. So now the question is how 5G can provide such performance, can support such services with ultra low latency, and of course also high reliability. So this is the first question that we are trying to answer. And the answer is actually simple, meaning that there are in particular two factors that are relevant to answer this question. First of all, the fact that, as we said, our cellular network is not just there to transfer data. Now it's there to process data and to store data. So this means that being able to process data, it can host indeed user applications and services for mobile users or for machines that are required by vertical industries. So this means that we have the so-called edge computing that you may have heard about clearly. And edge computing means indeed that we can compute so that we can have services at the edge instead of the cloud. And therefore, being now deployed at the edge, that means close to the mobile users, essentially where we have typically the base stations. Clearly, we do everything close to the users, close to the machines, and this reduces significantly the delays. So the other important factor that we need to underline is that in our networks, we now have this dominant approach that is virtualization. So everything tends to be virtualized. And by that, I mean network functions. So our typical network functions like switching or routing, they are actually implemented in software. And this means that in our network, we need CPU, we need memory, we need general purpose, essentially hardware, in order to implement these functions. And this means also that we can have, let's say, an abstraction of the network system. We can make this abstraction of the resources that are there, that at this point are not just networking, but also, as we said, computational, so CPU and memory. And this abstraction, you can think of it as a graph, essentially, where the different vertices of the graphs represent our network nodes, and the edges represent the links that connect these nodes. So this abstraction is actually built by what we call the SDN controller, where SDN stands indeed for software-defined networking. So this is just to say that our network, the 5G network, is actually a network where we have general, let's say, not customized hardware, and where the traditional functions are now implemented in software that is virtualized. And thanks to this controller, SDN controller, we can get this nice vision representation of the network resources. That said, from the point of view of the services that our vertical industries want to implement in our network system, there is also there the trend of virtualizing the services, and in particular to apply the so-called NFV approach. What does it mean? It means that given a service, any service application that you can think of, this can be decomposed in species, like a jigsaw puzzle, or like the Lego bricks that are shown in these slides. And the bricks are the functions, single tasks, single functions that can be composed together in order to get our nice service that is our castle in this representation. Now, clearly, this can be done with, let's say, some intelligence that in networking is called management and orchestration, but this is a detail. So what it matters is that services are now implemented, of course, in software. They are virtualized, and they are implemented by defining tasks, functions, and by connecting the different functions together. Now, why is this important? Because now we look at this rather complex slide, but actually it's not that difficult to understand, that essentially puts together the SDN and NFV technologies that we have introduced. So if you look at the bottom there, we have physical resources. Of course, we'll have networking, CPU, memories, but as we said, thanks to the SDN controller, we can abstract the resources that we have there. We can have this nice representation as a graph, let's say. If we look at the top of this figure, instead, there we have the industrial, the vertical services. And these vertical services, as we said, according to the NFV paradigm, can be decomposed in single functions that are called VNF, but again, this is a detail. So they are single functions implemented in software. Now, what we need to do in order to actually deploy a service, we need to map our virtual functions into the network resources. And we can do that by exploiting this graph-based representation, abstraction that we have of the network resources. So here, essentially, we have a mapping between the two. And this is the crucial point, because clearly now we need to ask ourselves how we can perform this mapping. Now, this mapping will be performed by the intelligent entity that, as I mentioned before, is called Mono in the network, and in particular by this orchestrator. So as we know, we are talking about in network, orchestration. We orchestrate resources, we orchestrate services, but actually means that we perform this mapping between the service functions and the network resources. Okay, so that said, this is the way in which we can actually deploy our services in 5G, network. And as we said, this is very important because in this way we can reduce the delay and the latency. And that's the only way, let's say, along with smart management of the radio resources, that allow us to reduce the latencies to values such as tens of milliseconds, or in some cases, even below 1 millisecond. Now, the other question that we should ask ourselves is how our network is able to host and deploy a wide range of services, each of which may have a different quality of service requirement and quality of service key performance, let's say, indicators to meet. Because you remember the triangle that we saw before, there are many different services that can be supported, and each of these services may indeed require a very different quality of service. So not just in terms of, as we said, the latency, but also in terms of throughput or number of connections. So here we have the solution. The solution and the answer to this second question is essentially network slicing. So what we do is the following. In the network, of course, we do not have an infinite amount of resources that are, let's say, so that we are able to meet all the possible requirements for all services, meaning that we cannot provide very high throughput, very low latency, lots of connections for all the services. That would require an infinite number of resources. So what we do is actually to partition the network resources, and then we consider, we assign each portion called slice to a certain type of service, and we configure those resources in that slice, in that partition, in such a way that we meet the quality of service requirement of that specific service. So for example, if for that service we request a very low latency, then we need to configure the resources in order to meet that KPI, in particular, that quality of service requirement. And then a different service, of course, will be assigned to a different slice. We configure the resources there accordingly, depending on what that particular service requires. For example, a high throughput. Well, then for that service, for that slice, we will just try to achieve high throughput, and so on. So this is essentially a context, the context within which we develop our solutions. And now I would like to focus indeed on a particular case that relates to smart factories, that is the digital twin. The digital twin use case is indeed one of the most popular that is nowadays considered in a 5G. So you for sure are aware of how it works, but very briefly, we consider that we have robots, and these robots may be mechanical arms as well as mobile robots that pick up boxes, drop boxes, and so on. These robots will send their coordinates, so the position essentially of their axis to an application, to a service that is deployed at the edge of the network. Of course, these coordinates will be sent through the radio access network, the base station, and will be processed by this digital twin app and interface that is essentially implemented in software. So it's one of those virtual functions that we talked about earlier, and that is in charge of creating the robot replica on a screen, so that the human supervisor can insert its commands through a joystick, and then these commands are essentially processed and translated into instructions for the robots by this motion planning and control VNF. That is the second virtual functions that composes our service. So this is an example where indeed the service is decomposed into two different functions implemented in software, so they are virtual functions. Now, the instructions for the robots are then sent back to the robots themselves through the radio access network. And this is essentially how the service works. Now, in order to ensure that we have a smooth control of the movements of the robots, based on our experiments and with a given, let's say, technology, of course, these values may change depending on these specific service implementation. But anyway, based on our experiments, we found that we can consider as a target latency for this first VNF 600 milliseconds, while for this second one, that is motion planning and control, 60 milliseconds. So this means that essentially when we have to process data at these VNFs, we need to stay below these target latency values for each of these VNF. So what are the challenges when we deploy these kind of services in our 5G networks? Clearly, the main challenge is performance to guarantee, as we said, the quality of service. But very importantly, the problem, as mentioned also earlier, is that at the edge, the amount of resources that are available, so CPU, memory, this amount is limited. And of course, if you think of a smart factory where we have to support several different services, not just, for example, digital twin, well, all these services implemented at the edge that covers the smart factory need to share the available resources. So using our resources efficiently is really critical. And that's why there is a large literature about the problem of optimally placing the VNF. That means to solve the mapping problem that we highlighted before, how to place the different functions that compose a service within the smart factory onto the available resources made available by the network. So given the graph representing the network resources, how to perform the mapping that we talk about. And of course, resources are costly. So we would like to use them wisely. And this is a big concern for both vertical industries and mobile operators. Vertical industries, because of course they have to pay mobile operators, and mobile operators want to provide their services, paying, of course, not such big money. The other important remark that we need to make here is that when we look at the performance, we need to ensure that this performance is actually met all the way from the edge to the robots and from the robots to the edge. So we need to consider both that the performance that we talk about are met not just at the edge of the network, but also over the radio link. So we are referring to that as the problem of ensuring that the KPIs, the key performance indicators that we care about, are satisfied end to end. And that's the end-to-end slicing concept. So now let me say something more about this end-to-end slicing, because we let's say, focused in particular on the virtualization of the vertical services for the smart factory, and we provided the digital twin as an example. But when we look at end-to-end slicing, we really need to account for all the components that are essentially in the path between the robots and the vertical service. So is vertical services and the virtualization of this vertical service the only thing that matters? So it is only the vertical service that consumes memory resources, and we need to essentially arbitrate the usage of these resources among different competing vertical services at the edge within the smart factory? Well, no, the answer is no, unfortunately, because we have to also consider that, as we mentioned, the network functions are now virtualized. So if you consider, for example, a base station, the base station will have the antenna and will have also the functions that are needed to transmit and receive data. But now these functions are implemented in software, so it means that they consume CPU and memory. And this is the same CPU, the same memory that also needs, that is needed by our vertical services implemented at the edge that covers the smart factory. So what I would like to highlight here is that the competition is not just among the vertical services that coexist at the edge, but is actually also with the more traditional, let's say, networking functions like transmission and reception, modulation, coding, decoding, and so on and so forth, that are now virtualized. So all of them consume CPU and actually memory. So we need techniques, solutions to wisely use all these resources among all the types, let's say, of functions that may need them. And as you may imagine, one of the most popular approaches nowadays is machine learning. So you can think of machine learning based approaches to actually allocate the resources. And since we need to do that end to end, we may need to have, let's say, a hierarchical structure where we care first, let's say, on the global resource allocation over the end-to-end path, and then we try to fine tune this resource allocation at the edge and over the wireless link. We can think of machine learning approaches that are implemented in a centralized manner, in a distributed manner. So there are, let's say, several possible solutions, and this is a very active research field that is actually quite interdisciplinary because it does not relate to networking only, it relates to services, vertical services as well, how to conceive them, and also to, let's say, computer science, meaning that machine learning, of course, here is involved, and we can think of different architectures for the machine learning. In this context, let me also mention a very interesting initiative that is the ORAN, the Open RAN. RAN stands for Radio Access Network. Essentially, according to the ORAN specifications, what we should have is indeed machine learning integrated essentially in our networks, different layers of the network system, and machine learning that essentially acts with different on a different time scale. So for a very dynamic, let's say, context and problems, we have certain types of machine learning models to solve, for example, the problem of allocating the resources over the radio link. But then we can also consider, let's say, a higher layer, so more general, let's say, problems with a different time scale. And in that case, we need different machine learning algorithms and so on. So this is just to mention that there are several interesting initiatives. ORAN is not the only one in the field of networking, where machine learning is essentially integrated in the network and is used to solve problems at different layers of the network structure. So let me also mention some recent work by my research group at Politecnico di Torino, where essentially we try to optimize the use of the resources through machine learning. And the framework that we have developed is called CAREM, that with respect to, let's say, state-of-the-art solutions, aims at handling heterogeneous wireless links. So by considering different technologies that can be used to connect our machines, our users to the network, 5G, let's say, and the new radio is not the only one that we can use. There are several different technologies. And when we have several different technologies, then of course, each of them essentially will be competing for the resources at the edge. So we try through CAREM, we try to start addressing this problem. And this is just to show you that our work is about developing a machine learning framework, but is also about developing a test bed. So whatever we envision is then implemented in a proof of concept in order to, let's say, verify that things can really work in practice. Let me move to the third, let's say, chapter of this presentation, that is about the, again, management of computing resources, but under dynamic service load. So here I go back specifically to the digital twin use case. And what I would like to, let's say, briefly sketch is an example of the problems that we need to face indeed when we deal with use cases such as the digital twin in our networks and the kind of solutions that we have developed. In particular, remember that, we said for each virtual network function, this VNF that compose the service, we have a certain target latency that is 600 milliseconds or 60 milliseconds. And clearly you can see from here that the most critical virtual function is the second one, right? The one that has got as target latency 60 milliseconds. So think of a flexible production line where the number of robots that we control may vary over time. Their tasks, of course, also may vary over time. So this means that actually the computational load on the virtual functions that compose the service will vary over time. And if it increases, then we may have problems in meeting the target latency at the virtual function number 2, that is 60 milliseconds. So what can we do in that case? Well, in that case, we need indeed to scale our service out. That means looking at the virtual function 2, we need to create a new instance for this function. And clearly, when instead the computational load decreases, then we need to remove those instances of a virtual function that are not necessary any longer. Why? Because remember that resources at the edge are precious. So we need to scale the service in That means indeed to reduce the number of instances in order to save resources. So now the problem is, how can we make such decisions about scaling out, scaling in? One idea, very simple, could be to use a thresholding algorithm. So if we know more or less, let's say, the CPU value that we cannot exceed, well, then clearly, let's say, monitoring that we will be able to trigger the scale out or scaling operation when necessary. And the same if we were able to measure the processing time, the processing latency at the virtual functions. As we approach, for example, the threshold of 60 milliseconds, then we could indeed decide to, for example, scale the service out. The problem is that these thresholds are not easy to compute. They depend indeed on the specific scenario. They depend indeed on the specific tasks or let's say activities that the robots also perform. So it is not, let's say, easy to capture these relations in such a way that we can have a simple thresholding algorithm in place. And even, let's say, for the latency, for the computation time at the virtual functions, it is not easy to measure this latency, as you will need to essentially inspect packets and so on. So I don't want to give too many details, but essentially it is not an easy task. So that's indeed an example where we need a machine learning approach, because this will allow us to, let's say, overcome the complexity of the problem and to capture the relation, the correlation between the different factors that play a role here. So this is indeed what we did. We used a simple random forest classification model. Of course, other models could be used as well. This is let's say, a preliminary work. So we used just a simple model, and we consider as input to this model the average CPU load that we have on the network functions, the number of instances of network functions that we have deployed, and we get as output the number of functions, virtual functions, that we should actually instantiate. So we know whether to scale out and how, or scale in and how. And this model clearly can be trained, pre-trained, and then we can run the trained model and make decisions about when to scale the service. So I just want to show you that this solution has been implemented in an actual 5G system architecture. This activity is indeed part of the 5 Growth European project that we have, and it is the result of the collaboration, of course, with the other partners. So we developed essentially this AI ML platform on the top left of the slide, where we let's say, upload the models, we train the models with the data sets, and now that we have a trained model, we give this model, we make this model available to the 5G architecture. For example, our service orchestrator that we mentioned earlier. And the service orchestrator will use this trained model to perform indeed to trigger the decisions regarding the scaling or the scale out of the services. So this is just to say that everything has been implemented. So it's something that it relates to real world systems. And in particular, this is the testbed that we used for the initial demo, using, let's say, the Politecnico AI/ML platform and the 5G architecture that has been deployed instead at CTTC, that is a well-known research center in Barcelona, Spain. And if you have a few more minutes, I would like to show you very briefly the part of the demo that we had. Here is also the link, and you can watch the whole video that is available.
So first, we proceed to instantiate the digital twin network service. While this process takes place, we will refresh some information regarding this service. Okay. So first of all, we will show the structure of the service. As we can see, it is composed of two VNFs connected by a virtual link. Okay. Now, while the instantiation takes process, we will see how it's evolving this operation. Now we can see that the status is instantiating. While instantiating, the different virtual machines implementing the VNFs and the virtual networks connecting these VNFs are created. Then the monitoring jobs gathering the related metrics of interest are configured at the monitoring platform. And at the final stages of the instantiation level, the service orchestrator interacts with the IML platform to download the model and the inference file to drive decisions, and also configures the rest of the data engineering pipeline. Here we can see that the service has been already instantiated, and we can see some information regarding this deployment as the service access point information, which are the external points that are offered by the different VNFs of the network service. We have also the flavor ID and the instantiation level. Finally, we have the dashboard info that will show the information that it's of interest to monitorize, to see the performance of the service and check its SLA. Okay, so now let's see the metric in the temporal evolution of the metric. Okay, now here we can see that we are monitoring the CPU load of the control VNF instances present deployed in the network service. Okay, this percentage is measured in, the y-axis represents the percentage of CPU load. And this is the relevant metric of interest because there is a direct relation with the processing latency associated to the commands that the robot sends to the system. Now, we're going to proceed to simulate the network service. With this graphical user interface on the right, we are interacting with the control app application, and we are starting two instances. We are emulating two instances of robots that are sending commands to the control app VNF. In a moment, we will see how this activity is translated in a change in the monitoring metric. This change is taking some time because we are representing the average of this metric over the last minute in order to avoid spikes in the metric and trigger false scaling decisions. Now we are going to proceed to provide more stress to the system in order to check that the inference job is deciding the suitable instantiation level regarding this CPU load, that is the metric of interest. So right now we have started a new instance of a robot. We have a total of 3 robots in the system, and we can see that there is an increase in the CPU load, in the average CPU load. Then in the meantime, the inference file the inference job is decided on the instantiation level. And once detecting the violation in the SLA expressed in the network service descriptor, it will trigger an scaling operation in order to solve this situation. Okay, so there is right now the scaling operation has been executed and it's been in process. While this takes place, several actions are done. First, the inference job is stopped. Then the new control app VNF is created, And finally, the inference job is start again, so we can continue deciding on the suitable instantiation level based on the metric of interest. Now,
okay, so I'm stopping in the video here, but just want to show you that essentially the whole system worked, and that was experimentally tested and demonstrated. So this essentially concludes my presentation, and the main message will be that indeed the edge computing is a very powerful paradigm that can provide very good performance to services that require low latency or that require to process lots of data that you cannot send, of course, to the cloud, but you have to keep local. And therefore, let's say, as we use more and more for more and more applications, the edge, well, the problem of resource allocation becomes crucial. And that's why we developed these AI ML driven solutions in order to optimally allocate the resources. As we said, the resources are needed not only for the vertical services, but also for more traditional network functions. So the system, the ecosystem, let's say, of the edge is very complex. And thanks to these approaches, we are actually able to let the system work well, meeting the quality of service requirements under dynamic conditions. That is indeed one of the most severe challenges that we have in our systems. So thank you very much for your attention, and I will be pleased to answer any questions you may have.
Thank you very much, Carla. Very interesting. I learned a lot because, as you know, I'm not exactly from the field. What we could do now is that I don't see open question, but I could ask a question, and then by the time we discuss this, if more questions appear, we can address them too. So, I mean, my question is more from the, let's say, AI, machine learning perspective. All the different problems, mainly about resource allocation that you mentioned, I wanted to know, I mean, from which approach of machine learning would you use? Are they all supervised learning issues, or some are supervised, some others are reinforcement learning, or is there another formal way to model it from the reinforcement learning setting? And then I wanted to ask you, in case they are supervised, are they data hungry, and where would you get the data set? If they are reinforcement learning, you need a sort of a realistic setting to do the training. So how, right, you see, so
Right.
from that perspective, how do you?
Right. Thanks a lot for this question. So we are using actually both. Let's say we used in this specific example that I showed, we used the supervised learning. And in this case, let's say the data are taken from our implementation, real world implementation. I didn't stress that actually, but you can see here the dashed orange line on the left that connects essentially the monitoring platform with the AI ML platform. So essentially we collect the data from the monitoring platform, we build the data sets, and then we use these data sets to train our models within the AI ML platform. So that's let's say the way that we envisioned the system. And but of course there are other cases where we use reinforcement learning. So for example, in the CAREM framework that I mentioned earlier, that is more focusing on the resource allocation on the wireless link, well, that framework is actually based on reinforcement learning. Reinforcement learning could be, let's say, considered also in this 5G architecture, let's say real world architecture that I'm showing here, because essentially here we have Spark and BigDL, and this is honestly what we have used so far and we have experimented with in the case of supervised learning. But actually Ray could be used for reinforcement learning. So through Ray, we could actually essentially simulate the environment, pre-train the reinforcement learning model, and then provide a pre-trained reinforcement learning model to the 5G entity that requires the model. Because as you know, even for reinforcement learning, it is actually important to pre-train the models before you actually make them work within a real world network. I don't know if I answered. If I may add just one more comment, very quick comment. So these, let's say, are the standard machine learning approaches, if you like, and of course, depending on the problem that you have, you may choose one or the other approach. The other interesting thing in that is, let's say, point of common ground, let's say, between our network and the I mean the networking issues and the machine learning issues is that robots, but in general any device or machine may be equipped with CPU and memory, and therefore able to let's say run part of the machine learning task. So if you consider, of course, training for supervised learning, every node, think in general of a wireless network where we have vehicles, we have pedestrians, that's in an urban environment. In the factory, of course, there might be also different types of machines. So, and each of them is collecting data. So they owns data, and they have CPU and memory, so they can do part of the job, of the training job, right? So that's the distributed, of course, machine learning architecture that we can think of. But one interesting research field is indeed how to map these machine learning tasks into the capabilities, also energy capabilities of the different nodes that are part of the system.
Carla, thank you very much.
Thank you very much for inviting me. It has been a pleasure.